So this video we're going to solve the same circuit now using Thevenin's theorem. Now you may remember that we generally had a Thevenin problem where I would say find the Thevenin equivalent of this circuit in this fashion. We didn't really use it directly to solve other problems like I'm about to, but I mean it still works. It's probably not the most efficient way, and so it's not something you would probably choose, but it's mainly just trying to show you that Thevenin does apply in terms of impedances here. So how are we going to do that? Well, the thing I'm looking for is the current through this resistor. So I'm going to choose those nodes to be the nodes by which I want to find the Thevenin equivalent, because I don't want to lose that part of the circuit. I want to collapse everything else down. And so I say, okay, I want to find my VOC and my ISC there. Well, why don't we start with the ISC? Because for the ISC, it's going to be a short circuit. And if it's a short circuit, that would short out these things over here. Nothing would happen on those. All the current would just go through the short circuit there. So makes my circuit much simpler here. We have 1 ohm. We have J, we have a current source, we have a voltage source, and this short circuit. I want to find my ISC. Well, how are we going to do this? We're going to say, okay, well, I mean, there's a couple options. I could do a source transformation and do it that way. Or I could do a node voltage or something like that, or other options. Probably I will just go ahead and do maybe source transformation. So I combine the current source. It's going to be 2 plus 2J, and we have this 1 plus J here, and then 6. And my ISC then is going to be the total voltage, which is 8 plus 2J divided by the impedance 1 plus J. So that gives me my ISC here. Then if I want to, I could, instead of finding my VOC, I could try to find the equivalent impedance. Now we can do this only because I have only independent sources in the problem. So we're allowed to do this. Remember, if you had dependent sources, it causes more problems on Thevenins. And the way you do this is you go ahead and remove your sources. And if I look at this, it's just going to be the 1 plus J parallel with 1 minus J, which we've seen before is just going to be 1 ohm. So that's my Z Thevenin here, not R anymore. It's my Z Thevenin is 1. And once I've got my equivalent there, then I can draw my Thevenin equivalent circuit, which is going to be a current source of my ISC, 8 plus 2J over 1 plus J. I have my Z Thevenin, which is 1. And then I also have the nodes here, 1 for my Thevenin nodes there, my A and B there, and I want to find my I0, and so I0 then is the total current by current divider times the impedance we're not at over the sum of the impedances. And we've done this algebra several times here. Should have it done by heart by now. It's going to work out to the same. I0 of t is 2.92 cosine omega t minus 31.0. Again, whether you really would want to do Thevenin's theorem for this, it's mainly just telling you that you can do Thevenin's theorem for this.